Power flow analysis helps keep your facility safely operating within its steady-state capacity and required voltage limits. Easily discern if load additions or change in equipment status will create an undesirable plant condition that compromises a safe work environment. Upon solving the power flow, we see several red highlighted equipment items indicating possible problems. Looking more closely, we see the cable feeding MCC 73 is near its rating, which is acceptable to us. The cable feeding MCC 74 is over its rating by about 35% and needs to be addressed. If we change the power flow options to showing current in amps, we can see that the cable feeding this MCC is loaded to 1534 amps. Now if we go back to the database and we increase the number of cables on this feeder to 5 and go back into power flow and solve, we see that we no longer have an overloaded condition. We see that it's acceptable. This overload issue has now created a work order to increase the number of cables feeding MCC 74. Transformer T50-C is right at its heating limit of nearly almost 100%. It's at 97.9%. We'll consider that to be okay for now and make a note for later review. Transformer T50-D is near its rating at 93.8%. Note that if we desire to add drive D2, however, that the transformer becomes overloaded and the voltage on the bus drops below 95%. This may force a transformer replacement or an operational constraint to never run all three drives together. On MCC medium 6 and MCC medium 7, conditions appear acceptable. However, if you remove all the motor load on the bus, you'll notice that the bus voltage increases over 106%. This indicates a need for over and under voltage protection. A low voltage condition drops motor contactors, creating a high voltage condition with capacitors left on the bus from when the voltage is restored. So apply a low voltage trip and lockout of the banks. A high voltage condition above 105% is easily created with capacitors left on the bus alone for any reason. So apply a high voltage trip and lock out the banks. The EasyPower power flow analysis tool helps you keep your facility operating safely and supplies important information to guide operational safe work practices. Harmonic Analysis helps you keep your facility from experiencing excessive distortion that leads to unexplained false trips, computer and PLC reboots, and equipment heating. At drive MCC1, accumulated drive harmonic currents create overheating in supply transformers. Here we see a 71.3% IEEE C57-110 derated capacity created. If loaded over 71.3%, this transformer will overheat. The voltage distortion is over 12%, which is far above a 5% desired value. Applying a 5th and 7th harmonic filter combination drops the voltage distortion to just under 6% and increases the derated capacity to 90.5%. At MCC2, we have a classic high distortion condition, which is created by a resonance due to a power factor correction capacitor connected on the bus. Voltage distortion is exceeding 20% and the supply transformer is derated to 57.3% of its capacity. This transformer is in a severe overheating condition. A frequency scan shows the resonant peak near the fifth harmonic, which is amplifying the harmonic currents being produced by 6-pulse drives on the bus. Replacing the capacitor bank with an adequately sized fifth harmonic filter releases all the capacity in the transformer and reduces the bus voltage distortion below 2%. Improve the safety, reliability, and efficiency of your electrical supply system by using EasyPower to minimize unsafe harmonic distortion levels. EasyPower coordination is the essential tool to help implement protection of equipment in your electrical supply system. Balance protection and selectivity while simultaneously visualizing arc flash hazard to provide safe and reliable continuation of process during fault conditions. After entering the coordination, simply select the portion of the system that you desire to coordinate and press the Plot TCC button. If you desire, adjust your one line to make it fit in the one line window better, and notice that the one line is automatically put onto the TCC. You can resize it to make it larger if you desire. You can also reposition notes for the protective devices. To show coordination with an active short circuit, double-click on the bus that you want to fault. Notice that the curves are automatically clipped according to the short circuit at the bus. If you want to add time differences to know how devices are timing, simply click and select two devices and add in a difference calculator. Notice that you can change settings on protective devices by simply dragging the portions of the curves. If you want to show arc flash levels right on the one line, at this location, click on the arc flash display button, and you can see that the arc flash is displayed automatically for the fault. As you modify the device settings, the arc flash levels will automatically update as well. You can drag these down to reduce the arc flash level even further. We're going to double click on this, and we're going to change the instantaneous pickup setting so we can reduce the arc flash level further. We can hit the apply button and see arc flash hasn't changed, but we added an instantaneous. Now we can drag the instantaneous left further and further and watch it decrease to level 2 and decrease to level 1 for our instantaneous. Once we've completed our coordination, we can now save our TCC. Upon exiting, you can also see a sequence of events of your protective devices that were involved in fault clearing. If you simply click on a bus and fault and click on the sequence of events button, you'll see that here we have miscoordination between these two devices. We can also get a report out by going to the PDC options, create sequence of events report, hit them, and toggle this, toggle it back on, and here we go to Window, and we have the sequence of events report. We see devices are not properly coordinated. EasyPower coordination supplies you with power, features, ease of use, and an extensive device library to coordinate your electrical supply system. Use the best coordination tool available to maintain and improve electrical safety in your facility. Dynamic stability analysis can be used to generate arc flash simulation results that include motor, cogeneration, and protective device real-time response. Arc flash methods, based on ANSI currents from a short circuit simulation, can generate significantly different results than seen in a real-time simulation where motor current decay and protective device staggered tripping is simulated. If we fault bus 4.16 MCC in dynamic stability, we see the quick decay in motor current on the bus and device tripping in 0.363 seconds. If we were to now change and go to an 85% arcing current, the trip time increases to 0.597 seconds. Stability results here show significantly reduced arc flash levels over accepted methods that do not include the real-time current decay effects of equipment for both the 100% and 85% cases. The real-time simulations show us why. If we fault bus MCC3 in dynamic stability, again we see the lesser but still present decay of the motor contribution. We trip quickly in 0.336 seconds. At 85% arc flash current, the fault time lengthens considerably to 0.812 seconds. The integrated method matches the 85% arc flash current instability the best. These are very close due to the minimal impact of the motor current decay, which is clearly visible here. If we fault bus switchgear 13.8 in dynamic stability, we see both a clear decay in fault current and protective device staggered tripping, where the fault current and accumulated energy drops significantly. Again, the integrated method comes closest to matching the decay and staggered tripping response. But the stability simulation reveals the true nature of the response. EasyPower Dynamic Stability provides the most accurate arc flash energy simulations available and brings visual insight to calculated results that were previously unavailable. Short circuit analysis is at the heart of breaker duty, arc flash, and coordination analysis. It is the essential engine. EasyPower Short Circuit utilizes fast, sparse matrix methods to perform fault calculations as fast as can possibly be done. To fault all buses in the system, enter Short Circuit and click on the Fault button. By default, all buses are faulted. Show momentary, interrupting, and 30-cycle currents together on the one line for a three-phase fault. Change the fault type to single line to ground. Show all phase currents. Now let's look at sequence components. Go back to a three-phase fault and show all the phase currents again. You can change between three-phase, single line to ground, double line to ground, and double line at will. We can also show over-dutied equipment right on the one-line diagram. The red ones are over-dutied breakers appearing right on our one-line diagram. Let's look at the momentary currents again. Let's fault a single bus, and here you can see all of the remote voltages and currents that are flowing on the system for this fault condition. We could make this a three-phase fault condition. Short circuit has many text reports, and we can use many of these different text reports to show different types of short circuit results. Now what we're going to do is do a fault all, and we're going to see the reports now. Okay, so here's the high voltage interrupting report. Here's the equipment duty report. Here we can see violations and warnings of breakers. Here's our low voltage interrupting report. There's many, many more reports. We can zoom out, go down here and select only a portion of the system and fault, and our reports will only show that portion. So here we see only the buses that were involved for the high voltage interrupting report. And for the breaker duty, only those breakers within that selected area that are in violation or have a warning.
Okay. EasyPower Arc Flash Analysis supplies the industry's most comprehensive arc flash evaluation. We include not only traditional single current traversal methods for arc flash computation, but include the first real-time simulated tripping of protected devices, the integrated method. Use these advanced tools and our complete integration of arc flash with short circuit and coordination to maintain and develop your arc flash safety program. We're going to enter short circuit to begin our arc flash analysis. Perform a fault on every bus in the system, and then show all arc flash results right on the one line. Zoom in to view the arc flash results. Results highlighted in red exceed a user settable threshold. Results for this case show values that include and exclude the main breaker. The results shown on the one line include the arc flash boundary and incident energy at 18 inches. One quick press of the F8 button displays and positions the arc flash hazard report. Notes show locations that exceed safe energy levels for energized work. Information shown in this report is used to calculate the incident energy and to determine the protective device trip time. Easily enter the totally integrated arc flash label editor and printer. Click on the selected devices. Select selected devices to show all labels to be printed. Use page up and down to show a label, and check or uncheck to include or exclude from printing. Custom design your label from a large selection of already developed templates. Select a template and then start your label editing process. This is a full-featured label design tool with conditional fields. Select the background and change its color to yellow. Save your updated edits into a new template. EasyPower integrates arc flash with short circuit coordination, label design, and label printing to make your arc flash analysis effort as quick and easy as possible. Reduce your arc flash study time so that you can spend time on delivering all aspects of your safety program.